Yeah, so we're switching slides here. So our second presenter today is Ray Jenkins. He is a veteran of both the and TCP/G research projects. He's done some work in wireless fingerprinting and secure boot for resource-constrained devices. But he's here today to talk about our ELFbac project and how we can prevent vulnerabilities. So take it away, Ray.
All right, thanks, Jason. Again, my name is Ray. I'm a PhD student here at Dartmouth, and today we are going to be talking about ELFbac and how we can use it to prevent, in general, vulnerabilities, but specifically we're going to be looking at a vulnerability that was found in OpenSSH. Again, for those who might not know, ELFbac is a project that we've had at Dartmouth for a couple of years now, part of our larger interest in language theoretic security. And so I will start first with kind of reviewing what ELFbac is and then move forward into what we actually did with OpenSSH. So as we begin, we can look at how our source code actually becomes a running process. Most of us will be familiar with this, but very quickly, we know that we can compile our code. We usually get object files. Depending on the platform that you are working on, the format for those object files and the eventual executable differs. So for Unix type systems, this is typically an ELF file, an executable and linkable format. If you're on Windows, this would be a portable executable, or if you're on OS X, that would be a Mako object. These object files really describe not just the contents of the executable that you have, but how that executable should be built in the process memory to get everything running and linked together so that everything operates correctly. At runtime, we have a linker that then takes, that executable that you've already built in this ELF format. It works with some external dynamic libraries like libc, and then poof, some magic happens and you get a running process. So we look at ELF in particular here. The other formats are very similar in their purpose, but ELF in particular, the files, again, contain the code and the data for your executable, as well as the metadata that you're going to use to determine where in memory the parts of your program go. So there's two important concepts with ELF, and that is sections and segments. So sections are something that most programmers would be familiar with, something like .text or .data. That is the sections of memory that contain the executable code that you will be running or the data that you will be manipulating. Each section within an ELF file contains semantically distinct units of code and data. That is, each section has permission controls, access controls that are specific to the contents of that section. Where this becomes interesting is when segments get involved. So part of the linking process involves grouping sections together to combine them into a segment. Segments are what actually get loaded at runtime, not the sections themselves. What this means is that for your average programmer, you have a mental model of how your executable, how your program works. For most of us, that means that in our address space, if we see something that's called read-only data, like RO data, we have this understanding that the data that's in that section should be read-only. What actually happens during linking and loading is that these sections get grouped together and their permissions get combined in often interesting ways. For example, read-only data actually gets executable permissions. Now, whether or not this has any external effect for your program entirely depends on the program itself. But in general, the point that I want to make here is that the intent of the programmer when they were building their software gets discarded by the packing of sections into segments. And this is the important part, right? We have a mental model, and that model, when it becomes reality, when you actually run a program, may not be what you think it is. So this is where ELF-based access control comes in. The whole goal is to reclaim this lost intent, the whole process of packing sections into segments to actually reclaim the information that is lost. So on the right, you'll see an architecture for ELFbac. You have some kind of legacy code that you want to ELFbacify, for lack of a better term. You've already compiled that code separately. You create a policy with our policy tool. The policy and the executable are then combined to create a single executable that contains a policy. When this executable is given to an ELFbac-aware loader at runtime, in combination with some kernel tricks, you are able to enforce the policy that you have created. Again, we're going to see policy later. But that's very much the idea, right? You compile some code, you write a policy, and then the kernel will enforce your policy for you. So looking at what an ELFbac policy is and how we create one, it's very simple. That the policy is just a finite state machine, which most of us are familiar with, where the states are defining particular phases of execution. So an example of this would be maybe input parsing. A lot of programs that take input, there's some section of your program that will deal with parsing that input. Maybe that is a particular state in this machine. The transitions between states are achieved either by memory accesses, that would be accessing a particular memory address or a particular piece of data, or function calls, which again at the low level is just accessing a particular address. When we get down to actually implementing this, how do we create a policy? The policies are just linker scripts. So if there's any programming language people or compiler people, you're probably familiar with what a linker script is. It's just a JSON file that defines what the sections are and what the relationships between sections should be. Whenever you're using GCC to compile a normal executable, there is a default linker script that the compiler uses on every platform that typically creates your .text section and your .data section. What we're doing with ELFbac is using these same mechanisms to create custom sections with custom permissions and custom interactions that work together to form an enforceable policy by the kernel. So you'll see on the right just a very simple example of the JSON that might create both a parser section that contains some kind of secret data and a transition from this parser section to some calculation section. The way that we combine a policy that is a linker script with the code that we have written is by using annotations for compiler pragmas. Very simply, it's just one line for functions or variables that you're interested in. By deciding what section this item, here we have a debug flag variable, and we are putting it in the input section. And that's really all that a policy is, or all that a policy consists of. So then how does it get enforced? Under the hood, what we do is we replace what the kernel sees as a virtual process's memory, or process's virtual memory, with a diversified collection of essentially page tables, right? So for the process itself, the process doesn't know that this policy is existing. It doesn't have any idea of what's going on. The kernel is in charge of both mapping the states that we have defined, the sections that we have created, and enforcing the transitions that we have defined. So policy violations end up being basically incorrect page table accesses. Whenever you're in the parse section and you want to go to the process state, there's a function transition that we've defined. The kernel is able to enforce that by looking at the permissions in page table entries, essentially. So now moving on to OpenSSH. Why did we look at OpenSSH? Well, first off, there are a dearth of devices out on the internet that are using OpenSSH. But for us in particular, there are a lot of devices in the IoT space and in the industrial control space that use OpenSSH and may not even know that they're using OpenSSH. There's just some headlines that I've included here. Millions of embedded devices are using the same private keys, or 12-year-old SSH bug exposes more than 2 million IoT devices. These were just big attacks that happened, I think, in 2015, 2016. But this goes all the way back to even 2010. We have some ICS cert alerts where it was very common for, and still is common for, people to port scan and look for OpenSSH installations that are using default credentials. And even this month, I found this Drives and Controls article. And I found this quote was really interesting. The company believes that its optional access to the Linux operating system through a secure shell will be of particular interest to OEMs. The title of this article is Groundbreaking Control System Brings Future to the Present. And one of their groundbreaking contributions is including OpenSSH, essentially. This really isn't anything new, and I'm not saying that OpenSSH shouldn't exist. I'm just pointing out that it's on everything these days, and it provides a very direct route for accessing machines, even if you don't know that you are providing that route. So in 2010, OpenSSH clients introduced some feature called roaming. And the idea was very simple. It was that as you are carrying on an OpenSSH session, if that session should get interrupted by network connectivity issues or something, you should be able to reconnect and continue your session as if the disconnect never happened. The way this occurs is by creating a buffer on the client side that will basically keep track of any commands that you enter on the client side while you are disconnected. Once you reconnect, the server will receive all of the commands that you have entered and then execute them as normal. In 2016, there was an information leak that was disclosed. And this was also pretty simple. The way it worked was that part of the key exchange for OpenSSH loads your SSH keys into memory. Part of the roaming operation creates this roaming buffer. Well, it just so happens that if you massage things correctly, you can get the roaming buffer to overlap the memory of the SSH keys. Now, the solution should have been very simple, and that is that the SSH keys should have been cleared from memory once they were no longer in use. However, this didn't happen. And the result was that after a disconnect and a reconnect, a server could convince the client to send them their roaming buffer, which could contain SSH keys. So this is the problem that we wanted to solve, and we felt like ELFbac was the best way to do that. So how could we go about doing that? The goal is to isolate the cryptographic keys from the region of memory that holds the roaming buffer, right? The way we do this, going back to a finite state machine, was to look at OpenSSH and try to determine how we could isolate these different sections. And we're not saying that this is the only way, but a very simple way was just to say that cryptographic code and network code should be in separate states. That is, the memory that they operate on should ideally be separate. The code that they're running should ideally be separate. So what we've created is three states: a start state, which also happens to be the kind of default execution state. If you're not doing network code in the packet state and you're not doing cryptographic code in the crypto state, then you are in the start state. After we decided on this kind of breakdown, it fell to deciding, or rather tracking down within the OpenSSH code base, what functions would cause transitions between these two, or these three states. This was just a matter of looking at the network code. Luckily, OpenSSH is very modular, so it didn't take long to identify the sections and the transitions that we needed. Now, within each state here I'm showing, what you're seeing is the address space according to that state. That is the visible space within that state. So for example, in the packet state, you see a roaming heap. So this would kind of signal that we're creating a separate roaming heap that is visible only within the packet state. It turns out that occasionally the crypto and packet, the states, the network code and the crypto code occasionally need to operate on the same data. To achieve this, we create a shared heap called the packet heap, where they can operate on shared data. So in total, out of the 100,000+ lines of code in OpenSSH, it only took 27 annotations, that is roughly 27 lines of code in 4 different files to implement this kind of state machine using the existing mechanisms of linking and loading and ELF files to actually achieve this kind of isolation. So what does this actually look like? Well, before we saw up in the right corner, you'll see the roaming buffer and the SSH keys, they all share the same space. With this policy in place, you'll notice that we have multiple heaps that are only visible to the particular states that we've defined. Again, this is enforced at the kernel level. So we have a crypto heap, a packet heap, a roaming heap, and then the default heap that everything else uses. And the way this works is that as far as the server is concerned, everything is transparent and is opaque, right? Or transparent rather, not opaque. So that the server is just going to continue requesting whatever's in the buffer. But on the client side, we are able to actually isolate what is in the roaming buffer from what is in the crypto buffer. So even if the keys don't get clearly removed in the crypto heap, they are still isolated from whatever is in the roaming heap. And any accesses outside of the roaming heap from roaming code would be caught by the kernel and not allowed. So I have a quick demo here. It's a video, but what you'll see is in the upper left-hand corner is an SSH server, a malicious SSH server that will be requesting all the data that it can get from the client. In the upper right-hand corner, you'll see 2 versions of the OpenSSH client. One that has an ELFbac policy and one that does not. In the lower right-hand corner, you will see just some information about the actual ELF files, just to show that one file has ELF and the other does not. And then in the lower left, you will see the actual information that we're able to obtain from the client through this, this process. So here we have 2 different versions of SSH. We're looking at the non-ELFbac version. It's pretty standard, pretty normal. Here we're running the OpenSSH server. And now we're going to connect using the non-ELFbac version. And we'll see that there is a connection resumed and a key that is exposed. So just quickly, you will see that roaming was enabled. A connection was established. At some point, the connection was terminated and then resumed. And then at the point that it was resumed, this is when we lost our OpenSSH key. So now we'll look at the ELFbac version, and just quickly on the ELF, you'll notice that we now have a separate program header for ELFbac. And a separate section for the policy that we have written. If we walk through this really quickly, you will see, again, roaming enabled. You will see a connection established. And then we see that once we get the connection resumed, we get a violation. That is, the server tried to access the cryptographic keys, or where it thought they would be, but the client was able to catch this. And that's basically the story. So, conclusions. Part of the LangSec in general is that we believe that the programmer intent is a crucial part of security. The idea is that your mental model should be what is actually executed in real life. ELFbac allows a programmer to codify this intent, create enforceable policy using existing mechanisms and very easy to do policy creation. So essentially, if ELFbac had been used in OpenSSH, this could have never happened. And then just more generally, ELFbac is as flexible as the software that it's trying to create policy for. So in the case of OpenSSH, it was very modular. It was very easy to separate the network code from the crypto code. This is not necessarily always the case. But the more modular software is, the easier it is to create this isolation. Looking forward to future work. So policy creation, as I mentioned earlier, there's a lot of intuition involved. That is, knowing what the program that you're modifying is doing, how it works, it requires a lot of that. So there's work to be done with understanding, maybe some static analysis could be useful in understanding the relationships among the functions and the data within an executable. Some of you may have picked up I haven't talked about performance, and that is because performance can be a problem with ELFbac. The larger your policy is, the more complex it is. It creates a lot of page tables and a lot of context switching, which can be very expensive. This is something that we definitely need to look into optimizing. Other things that we've looked at is multiple policies. So in a world where you have multiple black box pieces of software, multiple libraries that you may not trust, working together for a single executable, the idea would be that you could have policies for each different piece of the puzzle that you're putting together. The question is, how do those policies interact together? We haven't looked at that, but that's definitely something on the radar. And then where do we fit ELFbac into kind of IoT and ICS systems? We've talked to a couple industry partners, I think, looking for how they could fit ELFbac into their software stacks existing. So that's something that we're doing moving forward. And then lastly, just a teaser. Many of you probably heard about Spectre and Meltdown recently. We have some intuition that we could probably do something with Spectre. We don't have anything concrete to announce yet, but that is definitely something that we're working on, and we think that we can do this. And with that, that's all I have.